we'll turn to other ways of representing vectors in Python. I've told you that a vector is just a function from some domain D to a field. And we know how to represent functions in Python using dictionaries. So we're going to develop a class, a Python class called vec, with two instance variables, two fields. One is f, which represents the function using a Python dictionary. The other is d, which represents the domain using a Python set. And here we're going to adopt the convention that entries whose values are 0 don't have to be represented in the dictionary. This is our sparsity representation. So here's a kind of bare bones definition of a class that has these two fields. We can use this to create an instance by supplying two arguments, the set, the domain D, and the function f, represented as a dictionary. Now, we can assign this vector to a variable and access the two fields of v using a dot notation. Here's the code for the setter. It takes an instance v of vec, an element d of the domain of v, and a value, an element of the field. And it simply changes the dictionary, v.f, so that d maps to val. So we can use it in this way. Here's a quiz. Write the corresponding getItem procedure. It takes a vector v and a domain element d, and it outputs the value of entry d of the vec v. Here's the answer. If the domain element d is one of the keys of the dictionary v.f, then the procedure returns the corresponding value. And if not, return 0. Here's an alternative definition, a little less Pythonic. Now, why is this code insufficient? This code just returns the value that d maps to in the dictionary v.f. Well, this isn't sufficient because d might not be a key of v.f because of our sparsity convention. If the d entry of the vector v is 0, then d need not be a key of the dictionary. Now, earlier we gave the definition for a rudimentary Python class for vectors. Here it is. But we're going to code a much more elaborate version of the class that allows use of operator overloading for element access, scalar vector multiplication, vector addition, dot product, and so on. Here's a table showing the different operations that this class will allow for. Using this class, we'll be able to write much more concise vector code, such as this. This sets the A entry of v to 1.0. This assigns to the variable b the vector obtained by subtracting from the current value of b, a vector, a scalar multiple of v. And the scalar is the dot product of the current value of b with the vector v. And this prints the vector b in a nice format. You're going to code this class starting from a template that we provide. And the quizzes will help you know how to fill out the procedures. You're going to write the bodies of named procedures, such as setItem, getItem, add, and scalar multiple. Now, in actually using vecs, you're not going to use those named procedures. You're just going to use the operators. So, for example, this code instead of this messy code. In fact, in all your coding outside the vec module itself, you're not going to import those named procedures. You're simply going to import the class vec. And that will come along with all these operators overloaded. So in short, in code outside of VEC, just use the operators when operating on VECs. For each procedure you write, we'll provide the stub of the procedure. So for example, for add, here's the stub we provide. Now, this first line is a documentation string. It's basically a comment that tells us what the procedure is supposed to do. The second line is an assertion. It asserts, in this case, that to add two vectors, the domains have to be equal sets. Now, if this procedure gets past two vectors with different domains, it'll report an error. The assertion is there to remind us of a rule of vector addition, namely that you can't add vectors whose domains are different. So let's keep the assertion in the code, at least when writing procedures that use it for this class. Now, this vec class you write has got to be correct. You're going to be using it a lot. So we're providing a lot of test cases in a file testvec.py. So you can test your vec implementation using all these examples by just copying the examples into Python and seeing whether the result matches the results we provide in testvec. If they don't, something is wrong with your vec implementation, and you really have to figure it out and fix it. Now, once you think you've got something that works, you can run all the tests at once from outside Python in the command line by typing this command to a console. This is the name of whatever Python you're using, -m doctest and testvec.py. That will import your vec implementation from vec.py and run all the tests. And it'll print messages if some of the tests fail. So if nothing gets printed, you're good. All the tests have passed. The vec class is useful for representing vectors, but it's not the only useful representation. Well, we'll sometimes represent vectors by lists. A list of length n can be viewed as a function from 0 to n minus 1. It's easy to convert from a list-based representation to a dictionary-based representation such as vec. Write the procedure list to vec that takes a list of field elements and outputs an instance of vec with domain 0 through the length of the list minus 1, such that entry I of the vector v equals element I of the list L for each integer I in this domain. Here's the answer. Here's an alternative. This first solution uses this handy enumerate procedure, which allows you to enumerate over the pairs kx, where k is an index of into the list and x is the corresponding element. And this is using a more traditional loop in which we iterate through the indices into the list. The procedures 0vec and list2vec, which you've written in quizzes, are defined for you in the file vec util, which we've provided for you.